Hello everyone, welcome to Tuteetute. In this particular video, we will study about multi-layer transmission or multi-layer system. That means when the wave is traveling from one medium to other medium and those two media are separated by certain interface. In this particular criteria, we have studied the performance of the analysis. That means how the electric field is moving or how the electromagnetic wave is moving from one medium to other medium. While this movement is going on, how much amount of power is reflected back and how much amount of power is transmitted into the medium 2. These things we have studied in terms of reflection coefficient and transmission coefficient. Now what we are doing in the sense, instead of taking only one boundary means we are working with two media, medium 1, medium 2. But now we are going to see multi-layer. That means for our concept we are taking three media. So medium 1, medium 2 and here one more boundary is there, here medium 3. So like this we will take. Here medium 1 is there and this is the interface or the boundary between medium 1, medium 2. This is medium 2. Here medium 3 is there. This is the boundary between medium 2 and medium 3. This is the situation. Now how to analyze this one? That is what we need to see. So in case of multi-layer transmission, as I said now, this is the first boundary separating the two media, medium 1, medium 2. These are given with respect to these impedances eta 1 and eta 2. And here I am taking another boundary which is separating media 2 and medium 3. This medium 3 impedance is given by eta 3. So, and for our concept, we are restricted to only normal incidence. Studying oblique incidence in case of the multi-layer transmission is very difficult, and we will restrict our concept up to normal incidence only. So, we have transmitted or we have incident one electromagnetic wave normally on the boundary which is in between 1 and 2 media. Because of the impedance mismatch eta 1, eta 2, something will be reflected and something will be transmitted. Now this wave which is available in medium 2 coming from medium 1 will be incident on the boundary which is between medium 2 and medium 3. And because of the mismatch in the impedances eta 2 and eta 3, something will be reflected and remaining thing will be transmitted into the medium 2. And this process will be going on. Now it is coming like this and incidenting on this one. Again impedance mismatch is there, something will be transmitted, something will be reflected. Again this will be incident on this particular boundary. Again impedance mismatch is there, something will be reflected, something will be transmitted. This process is going on. Now how to analyze this one? For simple purpose, we will take transmission line analysis here. So this is actually semi-infinite medium. This is also semi-infinite medium. But this is the medium separating these two actually. Okay, so it is a finite length I am taking, its length is or its thickness is d. So we can compare these three media with respect to transmission line analysis. So first medium 1 I am taking as one transmission line having the characteristic impedance is eta 1. And medium 3 is another transmission line having the characteristic impedance is eta 3. In between these two, we have one more transmission line. Just for understanding purpose, I am taking with different heights. And here the new transmission line, that is medium 2 having its characteristic impedance is eta 2. Because it is of infinite length, its input impedance is also its characteristic impedance only, that is eta 3. Because it is of infinite length, its input impedance is equal to its characteristic impedance eta 1. But we cannot apply that one to this middle transmission line, that is medium 2, that is referring to medium 2. Because it is not infinite length, it is of thickness d only or its length is d only. Okay, this is what we can able to understand. And we need to analyze this one now for not having the reflections in the medium 1. We should not have reflections in the medium 1. For that purpose, can we get any condition for these three media? That is what we need to see. So we are studying about the multi-layer system, and in our concept we have three media, two boundaries, and three media impedances are given with eta 1, eta 2, eta 3. We compared that one with the transmission lines like this. Now what we need to do? We need to get the condition for not having the reflections in the medium 1. For that, what we need to do? That is what we are going to study. So what is the problem now? Reflections in the medium 1. Reflections in medium 1. That is the problem for us. We should not get any reflections in the medium 1. Now what is the solution for that particular problem? That is what we need to see. The solution will be like this. We need to do the analysis here. So as I said, here I am taking the transmission line analysis, what I told in the previous slide. So three transmission lines we are representing like this, representing the three media actually. So this is D. This is eta 1, this is eta 2, this is eta 3. Because it is of infinite length, its input impedance is equal to characteristic impedance. And here we don't know the impedance, that one I am taking as Z. First you get this Z value. Okay. First I will tell the approach, what we are going to do. Okay. And here, because it is of infinite length, here the input impedance is equal to its characteristic impedance, that is eta 1. Since I don't need any reflections in the medium 1, reflections related indicator is gamma. That means reflection coefficient. So for this particular transmission line, its characteristic impedance is given by eta 1, its load impedance is given by Z. The load impedance of medium 1, the load impedance of this transmission line 1 is, that means that is there here, it is the input impedance of this transmission line 2. Okay. By seeing this is the cascaded connection. So the input impedance of transmission line 2, that is this one, that is Z we are indicating. This is the load for transmission line 1. So for the transmission line 1, the characteristic impedance is represented, Z0 is equal to eta 1 and its load impedance is equal to Z. That is what we can able to tell. By having these things, I can write its gamma. Gamma is equal to ZL minus Z0 by ZL plus Z0. So it is equal to, what is ZL? Z minus, what is Z0? Eta 1 by Z plus eta 1. So this is the gamma for the transmission line 1. So our intention, what is our problem? Reflections in the medium 1. That means we need to make this reflection coefficient is equal to 0. That means we need to make this is equal to 0. That means we can get here Z is equal to eta 1. What is Z? We don't know. That is what we need to calculate. Okay. So Z is actually, so this is the approach we are going to follow. And by equating these two, we may get some condition for not having the reflections. Because here I have made this gamma is equal to 0. I made this gamma is equal to 0, so that I got Z is equal to eta 1. So eta 1 anyway, that is representing the transmission line 1. But what is Z? It is the input impedance of the transmission line 2. And for this transmission line 2, I have its characteristic impedance and the load impedance is eta 3. So by having the characteristic impedance and load impedance, I can get the input impedance from the transmission line theory. So according to the transmission line theory, Z input is equal to Z0 into ZL plus JZ0 tan beta L. L is the length of the transmission line, and in our case, length of this particular transmission line 2 is D by Z0 plus JZL tan beta D. This is the general formula. In case of the transmission line theory, input impedance is given by this particular formula, and we are looking for transmission line 2. And in case of this transmission line 2, what is ZL? Eta 3. And what is Z0? Eta 2. Substitute these things here. Then you will get its input impedance, and we are representing that one with Z. So Z input is equal to Z, and it is equal to Z0. What is Z0? Eta 2 multiplied with, this is ZL is eta 3 plus J eta 2 tan beta D by Z0 is eta 2 plus J eta 3 tan beta D. So this is what we can tell. It is Z. And this must be equated to eta 1 according to this reflection coefficient is equal to 0 condition. So if you make this is equal to eta 1, okay, I am using this particular condition, okay, eta 1 I am taking. Just to cross multiply these two and equate real values and imaginary values, then we will see what will happen. So I am writing here, I am cross multiplying for that eta 2 eta 3 plus J eta 2 square, and here we will get tan beta D. It is equal to, by cross multiplying, eta 1 eta 2 plus J eta 1 eta 3 tan beta D. This is what we got. Okay. So equate real parts. This one. What will you get? Eta 2 will be cancelled. Eta 1 is equal to eta 3 you will get. What is the meaning of this one? Eta 1, eta 3. Eta 1 is about transmission line 1. Eta 3 is about transmission line 3. These two impedances are same. That means these two media are same media. Okay. When you have these two media are same media, same type of media, then reflections will not be available in the medium 1. How it is possible? In between these two we have kept one particular transmission line or one different media is there. How it is possible means its length you should take as integer multiples of lambda by 2. From the transmission line theory we know the concept. When the length is lambda by 2, then whatever the impedance is there, that will be repeated. So here whatever the impedance is there, that will be repeated here whenever this D is equal to lambda by 2. Okay, then total transmission line will be having the same impedance, so that reflections are not possible. So this is one thing. But generally these three media are different media. At that time what will happen means, now you compare these imaginary parts also, equate the imaginary parts. So JJ will be cancelled, tan terms will be cancelled, so that you will get eta 2 square is equal to eta 1 eta 3. This is the condition we got. Now you see this condition involves three impedances. Eta 2 square related to transmission line 2, transmission line 1, transmission line 3. But if you see this one carefully, eta 2 is equal to geometric progression of impedances of medium 1 and medium 3. This type of relation is available for what type of transmission line? This relation is valid for lambda by 4 transmission line. So whenever this D is equal to lambda by 4, then what will happen? We have got this particular condition. This condition is related to reflection coefficient is equal to 0. So when you have this length is equal to lambda by 4, then no reflections will be coming into the medium 1. So you see this is very interesting. Okay, for not having the reflections in the previous concept we have seen about the Brewster angle. Okay, but that is in between two media. Even you have the three media, for not having the reflections in the medium 1, what you need to do in the sense, in the medium 2 you need to take the thickness is equal to lambda by 4. Okay, that means it is indicating quarter wavelength transmission line. So if that particular medium 2 having the thickness is equal to lambda by 4, then you will not be having the reflections in the medium 1. Okay, this is what you need to understand. Okay, so this is the criteria we can able to do in the multi-layer system when you have the three systems. Okay, three media, or we can able to work that one using the transmission line analysis. That means three transmission lines. So whatever the middle transmission line is there, whose thickness must be equal to lambda by 4. Okay, multi-layer transmissions and observations for not having the reflections. Okay, what is the observation we have made? Just now I have told that eta 2 must be equal to geometric progression. That means root of eta 1 eta 3. If you follow this one, then we will not be having the reflections. This is as simple as that lambda by 4 transmission line. For the lambda by 4 transmission line, you consider this is the Z0 is the characteristic impedance and load is the ZL, and its input impedance is Zin. Now you leave it about this multi-layer system, just to see this transmission line whose length is equal to lambda by 4. Input impedance, load impedance, Z0. Okay. What is the condition for Z0? What is the equation valid for the lambda by 4 transmission line? This is Z0 square by ZL, or Z0 is equal to root of Z input into ZL. This is what we have taken just now. This is for lambda by 4 transmission line. Now in our concept, now come to the multi-layer system having 3 media. 1, 2, 3. Forget about this medium, but it is having eta 3 characteristic impedance, so that its load impedance is eta 3, its characteristic impedance is eta 2, then its input impedance we can calculate now. Now this part is related to this one. So its input impedance we have taken as Z. For not having the reflections, what is required to be done here? This impedance must be equal to eta 1. That is what we have made. If the Z is equal to eta 1, then reflections will not come. That is what we have made. From that relation only we got here eta 2 is equal to root of eta 1 eta 3, similar to Z0 is equal to, Z0 is related to transmission line 2, that means medium 2. Zin is related to transmission line 1, that means medium 1. ZL is related to transmission line 3, that means medium 3. So this is not new concept. This is related to transmission line theory only. Lambda by 4 transmission line only. That is what I need to tell. Thank you.